What I want to point out here is, right, so when I'm doing these archetype problems, I typically start by trying to just work out what is in the square root here. So I'm first finding the derivative of my function x to the fifth over 10 plus 1 over 6 x cubed. And I rewrote it as x to the fifth over 10 plus x to the negative third over 6. Took the derivative using the power rule, 5x to the fourth over 10 minus 3x to the negative fourth over 6, and then simplified that a little bit. And then since I know I'm going to square it, I squared it. So be careful. So we really, like the square root of 1 plus the derivative squared, you can't simplify that unless you actually square out the derivative and add 1 to it. It's not just 1 plus the derivative, right? Just like the square root of a squared plus b squared is not just a plus b. So be careful, because I definitely saw more than one person make that kind of mistake on the quiz. So I like to multiply it out. So multiplying this out, I get the first thing squared plus 2 times the first thing times the second thing, which does end up being negative 1/2, plus the second thing squared, which is x to the negative 8 over 4. Finally, I add 1 to it, and adding 1 to all of this just changes the negative 1/2 to a positive 1/2. And then that factors back out as x to the fourth over 2 plus x to the negative fourth over 2 squared, instead of x to the fourth over 2 minus x to the negative fourth over 2 squared. So then finally, we're ready to integrate, right? Because now we're going to integrate the square root of this thing we just found, right? Because we're integrating the square root of 1 plus the derivative squared. So we put that in there to the square root, and the square root of this thing squared is just that thing. And then you have to anti-differentiate it. A few people forgot to do the anti-differentiating, just like, oh, I'm going to plug in 2 and plug in 1. No, we have to anti-differentiate and get x to the fifth plus x to the negative third and negative 6. You don't have to, so Mariah, I like your question. Sometimes we want to do that. It really, really depends on what we're working with. Things like this specific example, where I know the way the factoring is going to work is going to be that the middle term changes from a negative 1/2 to a positive 1/2. Typically, you don't have to make a common denominator. There are other problems where we really do, because the same sort of trick doesn't end up happening. But you can also make a common denominator here. It's just that it's more work than we have to do. But we can definitely, like, you totally could have done it that way. I just didn't, because I'm seeing that the 1 and the negative 1/2 I can just add together and get positive 1/2. And then the rest of it, yeah. The rest of it is just the part, I said you didn't have to do the rest, but like you plug in the 2 and the 1, you get some gross number at the end. Now, what I want to point out is that the surface area questions really aren't too much more work if we're careful. So surface area, before I scroll to the next page, right, when you're finding surface area, it's the integral of 2 pi times the radius times ds. We already know what ds is. No matter if we're going on the x-axis or the y-axis, ds is the square root of 1 plus dy dx squared, dx, which in this particular problem, ds is x to the fourth over 2 plus x to the negative fourth over 2. That is our ds. Excuse me, dx, I should say. So I want to really stress, and we'll do some more examples in a minute here. You can, when you're finding surface area, it doesn't matter what, well, I mean, it matters which axis you're going around, but no matter what axis you're going around, you can use whichever variable you want or are forced to use. In this case, we are forced to use the variable x because we have y equal to x to the fifth over 10 plus 1 over 6x cubed. And there is no way I'm able to solve for x as a function of y. So no matter if I'm revolving around the y-axis or around the x-axis, I know that my function y has to be in terms of x. So let's look at the next problem on the quiz. So the first problem said, find the area of the surface generated by revolving the curve around the y-axis. So if we're going around the y-axis, well, if you measure distance, and I know, like, so I'm going to drop my board a little bit. Hopefully you guys can kind of see this. So, right, if we're going around the y-axis, and we've got some curve here, the distance to the y-axis is measured as x. Just like the distance to the x-axis is measured as y. So if we're going around the y-axis, the radius is x. And so the integral of 2 pi r ds is 2 pi times x times ds, where ds is just the thing we found in the previous part. And then we have to multiply the x through before we can integrate. So we get x to the 5th over 2 plus x to the negative 3rd over 2, and then we anti-differentiate that and get x to the 6th over 12 plus x to the negative 2nd over negative 4. And then the rest of it's just plugging in, which I don't really want to focus on right this moment. I do want to point out that for the surface area revolved around the x-axis, well, if we're going around the x-axis, the radius is y. But now we're still in terms of x, right? My integral is 2 pi r ds. It's 2 pi integral of y times ds. I can't do my ds in terms of y. I wish I could. I can't. I can't solve for x as a function of y. I can't find dx dy or g prime of y. So instead, well, if I'm going around the x-axis, my radius is y, but I know that y is equal to, sorry, I'm going to go back, y is equal to this function. So whatever y is, if I know what x is, then I know what y is. So I'm going to go back, and for around the x-axis, I'm going to substitute in y equal to x to the 5th over 10 plus 1 over 6x cubed for my radius. And my ds is still the same as it was before. And then before I can integrate, I have to multiply this whole thing out. And if you looked at the solutions earlier, I actually had a mistake. I fixed it. But we multiply this out, we get x to the 9th over 20 plus x over 20 plus x over 12 plus x to the negative 7th over 12. And then the rest of it is just terrible arithmetic of integrating and getting some really disgusting number, which I think is right, but I'm sure it's possible there's a mistake there. But the real point is here that if you're going around the x-axis, the radius is y, but if you're doing your integral in terms of x, you replace y with what x is equal to. Sorry, you replace y with what is equal to in terms of x. Okay. So before we start doing more examples, are there questions about the quiz? I will definitely say if you have questions later, feel free to look at the quiz solutions more. If you still have questions, feel free to ask me because I'm happy to explain anything I've done here. Let me go ahead and grab the stuff I wanted to do. So people definitely still have questions about arc length, which I want to cover. And let me I have 3 examples I want to do, one of which is a homework question that 2 of you asked me about. Let me go back to this example here. Don't want, those are all terrible. Sorry, there's I thought I had an example that I wanted. Sorry, one sec. There we go, okay, cool. So let me start off with another example like the one we did. And I'm gonna talk about both surface area and the other thing. Sorry, arc length and surface area. So let me pin my video. Okay, cool. All right. So we're going to do mostly setup. I'm going to focus less on evaluation just because most of these get pretty messy after we've done the integration and started trying to actually plug in points. But let's look at this problem here. I want to find the arc length of the function x equal to 3y squared minus 1/24 natural log of y for, I usually pick 1 and 2 just because they seem easy. You can pick any limits of integration as long as the function is defined. So I can't pick 0, but I can pick for y between, let's do 1 and 3 just to be crazy. All right. And I should say arc length, right? Arc length. Okay. So we know the setup. We know the setup is arc length is the integral from 1 to 3, in this case, of ds, which is the integral from 1 to 3 of the square root of 1 plus the derivative of your function. So I'm going to write dx dy squared. And then it's got to be dy because it's a function of y. Or you can also say the dy is on the bottom, so it's going to be dy. And now I have to find my dx dy in square root. Now here's the thing. This one looks like the usual kind of thing is going to be usual. The trick thing is going to happen where once you differentiate and square it, you're going to get a negative 1/2 in the middle. So let's take the derivative here. My dx dy is 6y minus 1/24 times 1 over y. And now I don't want to put this in there right now. It could definitely write it like this. I can say, okay, I got the integral of 1 to 3 of the square root of 1 plus this, which is 6y minus 1 over 24y squared. But writing all of this out every step, I'm sorry, that's a 3, is a lot. Yeah, thanks. Yeah, thanks, Sophia. So I don't want to write this out every step. I'd rather simplify all the stuff inside the square root and then at the end write the whole integral. So I'm going to do that. So I'm going to square this to dx dy squared. So when I square this, well, I'm going to get 6y squared plus 2 times 6y times negative 1 over 24y plus 1 over 24y squared. And I'm just using the knowledge that when you square some binomial thing, it's the first term squared plus 2 times the first and the second plus the second term squared. So this ends up being 36y squared. The y's here cancel. 2 times 6 is 12. Times negative 1/24 is negative 1/2. And then I get plus. I don't really want to square this out. I could. It is 1 over 576y squared. But the point is, once I see that negative 1/2, I know things are going to factor back out. So I really don't want to do any more work than I have to. So then I'm going to add 1. So what I'm going to see is that this, so 1 plus this is going to be the integral from 1 to 3 of the square root of 36y squared plus 1/2 plus 1 over 576y squared. And here's the deal. This factors. This factors exactly like this squared, except the middle sign is positive now instead of negative. So this is going to be the integral from 1 to 3 of the square root of 6y plus 1 over 24y squared dy. I really want to make sure everyone's cool with this, because this is kind of like the crux of what's happening here. We multiply this out, we add 1, the middle changes from negative 1/2 to positive 1/2, and then it factors back out the same way it was before, except now the middle sign has changed, in this case from negative to positive. You have to be able to do that to make this work. And then this ends up being, sure. So the square root of this stuff squared is just the stuff. So this is the integral from 1 to 3 of 6y plus 1 over 24y dy. And then I'm going to go up here, since I'm running out of room. The integral of 6y is 6y squared over 2, which is 3y squared. And the integral of 1 over 24y, or 1 over 24 times 1 over y, is 1 over 24 times the natural log of the absolute value of 1. From 1 to 3. And so look, we've gotten essentially almost all the way back to where we started. Right, except our function, our answer, before we plug in the integration, is our original function, except the middle sign has changed from negative to positive. Yeah, Kimberly, the being squared and the square root totally undo each other. The square root of something squared is just the something. Yeah. There is something, we do have to be a little careful, because technically what I have here is the absolute value of 6y plus 1 over 24y. But since this expression is always positive between 1 and 3, there's no issue about it being positive and negative, so we don't worry about the absolute value. So then we plug in 3, and I'm not going to finish, I'm going to get 6 times, well, this is 3y squared. So I'm going to plug in 3. And we get 3 times 3 squared, which is 27, plus 1 over 24 natural log of 3, minus, I'm going to plug in 1, and 3 times 1 squared is 3, plus 1 over 24 natural log of 1. Natural log of 1 is 0. So this ends up being 27 minus 3, which is 24, plus 1 over 24 natural log of 3. Not very nice, but fine. But now we can ask 2 really easy questions to set up knowing what we know. So here's what I know for this. I know that for x equal to, oh, what's it, sorry, 3y squared minus 1 over 24 natural log of y. I know that ds, which we just found before, and ds is the square root of 1 plus dx dy squared, dy, that's this. That's my ds. I feel like I'm talking about Nintendo, but I'm not. That is my ds. It's the small arc length segment. And so now when I start talking about surface area, right? For surface area is the integral of 2 pi r ds. That's the ds I'm going to use. I'm not going to go through the whole process of doing the square root of 1 plus the derivative of the square root again, if I'm using the same function. So I know that ds is equal to that. 6y plus 1 over 24y dy. Right, that y is in the denominator. And yes, you do need the dy or the dx if it's in x. Okay, so what's the surface area of this segment revolved around the x-axis? And if you're going around the x-axis, your radius is y. Okay, because if you're thinking, and again, we're thinking, I've got this segment, and I'm going around the x-axis here like this, and the radius, the distance to the axis, well, that's a y distance. Is it y squared? Sorry, the ds part? Is that what you're asking about? So I'll just say that opens. So x is 3y squared minus 1 over 24 natural log of y. And ds is 6y plus 1 over 24y dy. I don't think it's y squared. Now you got me. No, it's just that. 6y plus 1 over 24y. If we anti-differentiated it, you get the square. Or the differentiated the square, sorry. So, for surface area around the x-axis, I'm just using this formula. And again, we've got y between 1 and 3. So, surface area around the x-axis is going to be the integral from 1 to 3 of 2 pi times the radius, which is y, times the ds, which is this thing right here. And then before I can integrate, I have to simplify. I'm going to pull out the 2 pi. And y times 6y is 6y squared. And y times 1 over 24y is just 1 over 24. So then we would integrate, and we would get 2 pi times the integral of 6y squared is 6y cubed over 3, which is 2y cubed. The integral of 1 over 24 is 1 over 24y. Not in the denominator, but 1 over 24 times y from 1 to 3. I'm going to stop that one there because I don't think plugging it in is really showing us a whole lot. On the other hand, if we go around the y-axis, if we go around the y-axis, our radius is x. So we're going to do the integral of 2 pi times our radius times our ds. But the problem is our ds is still in terms of y and cannot be changed. Sometimes there are functions that you can do either way. This is not an example of that. So in this case, what we have to do is we have to say, well, I can't change ds to be in terms of y, sorry, to be in terms of x. So I'm going to turn x to be in terms of y. So I'm going to write this as 2 pi times the integral from 1 to 3 of x. There's x. It's 3y squared minus 1 over 24, natural log of y. And we might have a problem here that I hadn't anticipated. It's all right. We might not be able to finish this problem. It's okay. So I'd have 3y squared minus 1 over 24y times the ds, which is still the same. It's still this 6. Oh, sorry, I wrote 1 over 24y. It's 1 over 24 natural log of y. Apologies. Made a small mistake there. Times the ds, which is still the 6y plus 1 over 24y. Now we can't actually integrate this because we don't know how to integrate the natural log of y or the natural log of y times another thing. That's something we'll learn in chapter 7 when we start talking about integration by parts. But I will say this is integrable. We just don't have the tools to do it yet. So this is totally doable. We'll learn how to do it later. But I really want to point out, if you're going around the, well, so actually, yeah, I'll leave it there. So for this problem, since our function was in terms of y, going around the x-axis meant our radius was just y. Going around the y-axis meant our radius was x, which we had to turn into the function of y. Okay. Let's look at another question. Let's see. Let's look at this one. So please chime in if you have questions or type in. I just don't always see them as fast. That's quite a lot there. So let's look at something like, we can do u or we can do u. I think we should do u. So what if my function was f of x equal to the square root of 2x plus 1? And I want to find the surface area going around both axes. So let's first go around, the y-axis. And, oh, sorry, I forgot what x is between 1 and 7. 7 seems like a terrible choice, but maybe it works out nicely. So surface area. All right, so again, when I hear surface area, I think integral of 2 pi r ds. And we're going on the y-axis. Whatever axis you're going around, your radius is the other variable. So if you're going around the y-axis, your radius is x. It's going to be 2 pi, sorry, integral 2 pi times the integral of r, which is x, ds, which we'll have to deal with, right? So let's deal with the ds first. I really, as you can tell, I don't want to write the integral like 5 times when I'm simplifying ds. I want to do all my ds simplifying over on the side and then just plug in the nice result to my integral because it's just going to be less writing. So let's see, I know that my ds is the square root of 1 plus the derivative squared dx. So my derivative, so this is 2x plus 1 to the 1/2. The derivative f prime of x is 1/2 times 2x plus 1 to the negative 1/2 times 2. The 2's cancel. Great. That's just 2x plus 1 to the negative 1/2 or 1 over the square root of 2x plus 1. So f prime of x squared is going to be this thing squared, which will be 2x plus 1 to the negative first, or if you prefer, 1 over 2x plus 1. And so I'm going to be working with 1 plus 1 over 2x plus 1. And I think this is the thing that someone was asking about. Is like, don't you get a common denominator? Yeah, for this problem, I'm going to get a common denominator. So I'm going to get 1 plus 1 over 2x plus 1. That feels, something feels wrong about that. But now I'm concerned. Oh, I know. Okay. This one we might not go around the y-axis or the other axis. Actually, so I will point out this one I don't think we can do around the y-axis. Well, let's go ahead and set it up and see what this setup looks like. Yeah, sometimes one axis is way easier to do than the other axis. Let's check it. So I'm going to simplify this as, or get a common denominator. So I've got 2x plus 1 over 2x plus 1, which is 2x plus 2 over 2x plus 1. Yeah. Okay. So that's what we have right here. The square root of 2x plus 2 over 2x plus 1. And at first glance, I will fully admit, I'm not really sure how we should go about doing this one. Yeah, do that. Yeah, I think this problem is terrible. So we'll come back to this one because there is something to say. Just like 2x plus 1 over 2x plus 1. 2x. Oh, well, it's kind of like it, except not exactly, right? It's 2x plus 2 over 2x plus 1. Right, so are we asking what I'm adding, right? And this is what I'm doing here, right? That's 2x plus 1 over 2x plus 1. So then I added it to 1 over 2x plus 1. Yeah, exactly. There you go. So I think we're kind of stuck here, but we'll come back in a minute. On the other hand, let's talk about going around the other axis, the x-axis, because that one actually will work out very nicely. So the only difference between going around the y-axis and going around the x-axis is the radius. So if I was going to go around the x-axis instead, I would be doing 2 pi times the integral from 1 to 3 of my radius, which is y, times the square root of 2x plus 2 over 2x plus 1 dx. So in this case, y is equal to the square root of 2x plus 1. So I'm going to rewrite this on the other side of the board as the integral from 1 to 3 of the square root of 2x plus 1 times the square root of 2x plus 2 over the square root of 2x plus 1. Okay. So we're going to write y, which is the square root of 2x plus 1. Drop a pen cap there. Square root of 2x plus 2 over 2x plus 1. And now here's the thing. This square root of 2x plus 1 and that square root of 2x plus 1 cancel out. Right? You can totally rewrite the square root of this over the square root of that, or should say the square root of this over that as the square root of 2x plus 2 over the square root of 2x plus 1. I don't know why I keep writing 1 to 3 when I totally said the limits were from 1 to 7. I think the previous problem was 1 to 3 and it just got it stuck in my head. So I should be writing 1 to 7, not 1 to 3. Sorry. There we go. That. So this cancels with that. And then we're trying to do the integral from 1 to 7 of the square root of 2x plus 2. And now we can just do a u substitution. You can say, oh, u is 2x plus 2. Du dx is just 2. So du over 2 is dx. So we can rewrite this as 2 pi times the integral of the square root of u, or u to the 1/2, times dx, which is du over 2. And that 2 will cancel that 2. I'm also going to change my limits of integration. If x is 1, then u is 2 times 1 plus 2, which is 4. And if x is 7, u is 2 times 7 plus 2, which is 14 plus 2, which is 16. And then things are going to work out pretty nicely. You can, Mariah, I'm definitely cool with the fact that you can do the integral of this. The only thing you have to be careful of is if you just do the integral straight away and say it's going to be, 2x plus 2 to the 3/2 power divided by 3/2, which is times 2/3, you also have to divide by the coefficient of x, which is 2. So yes, it is fine to do it that way if you're comfortable with that, but not everyone, I think, is comfortable necessarily doing it that way. Just remember, right, when you've got a coefficient of x there, you have to divide by that coefficient. So I'm going to get 2/3 u to the 3/2 from 4 to 16, which is going to be 2/3 16 to the 3/2 minus 4 to the 3/2, which is going to be 2/3. Let's see, 16 to the 3/2 is 64, because it's the square root of 16, which is 4 cubed, 64. And 4 to the 3/2 is 8. So you get 2/3 of 64 minus 8, which is 2/3 of 56, which is 112 over 3. And of course, I forgot the pi. I always forget the pi. How disappointing. Sorry, there's a pi there. So it's 112 pi over 3. I didn't forget the 2 pi because we canceled the 2. But I do feel like this kind of, the previous problem, I think, still deserves to be answered, or at least explored. I should say, are there other, so just to point out, if you did do it this way, it would totally work out the same way, right? If you plug in 7, you get 2 times 7 is 14 plus 2 is 16. You get 2/3 16 to the 3/2, which would be exactly this 2/3 of 64. And the 1/2 of the 2 pi we cancel. So yeah, it would work out the same. But you might be curious, well, what if they did want me to go around the y-axis? And I tried doing this, and this might, so this integral is probably manageable in some way. There's probably some funky u substitution or something, or maybe, I don't know. But I do think, I'm not 100% sure, I'll warn you, this path might lead to disappointment. We might find that there is not a good way to do this. I don't think that's the case, but sometimes problems just don't work out that nice. But let's go ahead and try. And so the thing you can try is, if you try going around a particular axis and it doesn't look like it's going to work out nice, if you can, so we couldn't have done this for the previous problem we did, where we had y or x equals y squared or whatever with plus natural log of y. There's no way to solve for y there. Here, we could totally rewrite this in terms of x as a function of y. I can totally, and I really want to, yes, I'm going to erase all of this. And so we're not doing that. Erase all of this. Instead, what we're going to do is we're going to say, well, I can do this in terms of y. I can say, well, this is y equals the square root of 2x plus 1. I can square both sides. And I can solve for x. Y squared minus 1 times 1/2 is equal to x. And then instead of doing the integral like this as 2 pi r ds, I'm going to do it as 2 pi integral. So if I'm going around the y-axis, the radius is x. So there's my radius. Times ds, which I have to find. Where ds is going to be, so again, I'm going to do it in terms of y. So it's going to be the square root of 1 plus dx dy squared. So the square root of 1 plus dx dy squared. And again, I really don't know if this is going to work out. Fingers crossed. So let's take the derivative here. So fortunately, this is pretty easy to take the derivative of. The derivative of 1/2 y squared is 1/2 times 2y, which is just y. Oh, we're so close. I think this isn't going to work out, unfortunately. No, yeah. So it's the square root of, yeah, that's my derivative squared. It's y squared, yeah. Yeah, so we end up with something we also can't do. That's too bad. Yeah, we would need other methods to be able to handle this. This is probably a trig substitution problem. So yeah, some of these problems just don't work out so nicely. Apologies for doing one that isn't nice. Let's look at one that is nice. Although I bet a lot of you think this one is not really nice. So a couple of you asked me a couple different questions about this e to the x plus e to the negative x, so the 2 thing. And there's actually, so there's 2 different versions, and I feel like we should probably address both of them. And then after that, we'll move on to talking about force and work and all that kind of stuff. So the way so I feel like one of these is much harder than the other one. I don't know, maybe not. So here, and I'm going to do it in terms of x, even though someone asked me. So here are the 2 different questions. The first question is, we've got y equal to e to the x plus e to the negative x over 2. And x is between negative c and c. And we know that the arc length of this, so you've got so this looks kind of like this. Kind of looks like a parabola, it's not a parabola. So here's what the problem is saying. Here's negative c, here's c. What the problem is saying is we know the length of this is some number. So this arc length is, I'm going to use a different number just because I will use it. So the arc length is 6. They're asking, if the arc length of this is 6, what are the values of c? Or what is the value of c? So basically the idea here is we have to set up the formula for arc length. So the arc length is going to be the integral from negative c to c of the square root of 1 plus dy dx squared dx. And we're going to set that equal to 6. And then we're going to solve for c. Now, here's the thing I really want to say about this. This ds here is actually much nicer than you might know it is. So raise of hands or other thing. So let me ask for volunteers. Have any of you heard of the hyperbolic trig functions? It's really okay if you haven't, but I'm just curious if you have. So you can type yes or no. You can do the thing where you raise your hand or do a yes or a no. Hearing some yeses, some nos. Okay, they mentioned it but didn't explain. All right. Okay, so how much time do we have? All right. Here's the very, very abbreviated version of hyperbolic trig functions. Hyperbolic cosine is this function. So we write it as cos h of x, and it's defined to be e to the x plus e to the negative x over 2. In a similar way, hyperbolic sine of x is e to the x minus e to the minus x over 2. You could write these all the time. The only reason we give them these other names, well, there's 2 reasons we give them these other names. 1, it's more convenient to write this than it is to write this. But 2, the hyperbolic trig functions, their derivatives act in a very similar way as the regular trig functions. Let me show you on the other side here. And there is a reason for talking about this, I promise you. I'm not just doing this because I think it's interesting. So if I look at hyperbolic sine of x, which is e to the x minus e to the minus x over 2, or I would actually probably write it as 1/2 of all that. What's the derivative of that? Well, the derivative is 1/2 times the derivative of e to the x is e to the x. The derivative of e to the negative x is e to the negative x times -1. So we get a plus e to the negative x, which is hyperbolic cosine. And in an almost exactly similar, but not quite the same way, the derivative of hyperbolic cosine, which is 1/2 e to the x plus e to the minus x, that derivative is, well, 1/2 times the derivative of e to the x and e to the x. And the derivative of e to the negative x is negative e to the negative x. So the derivative of hyperbolic cosine isn't negative hyperbolic sine, it's actually positive hyperbolic sine. But I will stress that these are very much the same as how the regular trig functions work. Right? The derivative of sine is cosine, the derivative of cosine is negative. The derivative of hyperbolic sine is hyperbolic cosine, the derivative of hyperbolic cosine is positive hyperbolic sine. Now, the thing that's cool is that the rest of the trig functions, the rest of the hyperbolic trig functions work the same. Meaning, the derivative of hyperbolic tangent is hyperbolic secant squared. The derivative of hyperbolic cotangent is hyperbolic cosecant squared with a negative. The derivative of hyperbolic secant is hyperbolic secant hyperbolic tangent, and so on and so forth. The only thing that's different is the following. For the regular trig functions, the co-functions, cosine, cotangent, cosecant, all have negative derivatives. And the other ones, sine, tangent, and secant, all have positive derivatives. For the hyperbolic trig functions, it's not the co-functions and the non-co-functions, it's all the ones on the left. Hyperbolic sine, hyperbolic cosine, hyperbolic tangent, that's why we write them that way, have positive derivatives. And hyperbolic cosecant, hyperbolic secant, and hyperbolic cotangent all have negative derivatives. But they're still the same as what we'd expect them to be the other way. So I don't want to spend too much time talking about this because I really just want to show you one other thing. And that's the fact that there is a hyperbolic trigonometric identity. We know that regular sine squared x plus regular cosine squared x equals 1. Well, there's a similar hyperbolic trigonometry, which is the following. Hyperbolic cosine squared of x minus hyperbolic sine squared of x equals 1. I would encourage you to show it to yourself on your own. It comes from squaring this, so it's 1/2 e to the x plus e to the negative x quantity squared minus 1/2 e to the x minus e to the minus x quantity squared. That is equal to 1. If you multiply this out, you'll get an e to the 2x and e to the negative 2x with a coefficient. Here you'll get an e to the 2x and e to the negative 2x with a coefficient, and all those will cancel. And here you'll be left with plus 1/2, and here you'll get a minus 1/2. Those will add together to give you a positive 1. Okay, so now, with this in mind, that the derivative of hyperbolic sine is hyperbolic cosine, and the derivative of hyperbolic cosine is hyperbolic sine, let's go back to this problem. So let's see. My function here is hyperbolic cosine. Its derivative is hyperbolic sine. And I feel like I'm about, oh yeah. And this is definitely the harder of the two problems that were asked by you guys. The other one we're going to talk about is much easier. So, I'm a little worried about this problem now because this looks terrible. Let's see, let me make sure I'm reading right. Yeah. Given hyperbolic cosine of h from x between the so here's what we're doing. Eesh, I'm genuinely worried because I was hoping something was going to happen, but it's not. So here's what we've got. We've got that we want 6 to equal the integral from negative c to c of the square root of 1 plus hyperbolic cosine squared. Hyperbolic sine squared. And the problem with this problem is that this is really not nice. I think I've done this integral before. It is kind of absolutely terrible. So this one you can't do the nice thing I wanted to do, which was use some sort of identity. I think it does work out for the other one all right. But, oh boy, yeah, that's awful. So instead, what you have to do here, oh man, so you probably would have to actually just do, so where are these problems from? That's a good question. I don't remember who asked them. Whose class are these from? Geez. I guess I would write it out like this. Square root of 1 plus. So if I actually square the derivative of this, which is 1/2 e to the x minus e to the minus x, if you square that out, you get 1/4 e to the 2x. I feel like this is supposed to work out all right. Maybe I'm dumbly forgetting something. Yeah, maybe I'm really, really not smart. Sorry, it's not that I'm not smart. It's just that I've forgotten something that I think is easy and I shouldn't have forgotten it. I was totally on the right track. There's an identity for this. I'm just missing it. Add this over there. So yeah, we're good to go. So what I will say is you can write it this way. So that 1 plus hyperbolic sine squared is equal to cosine squared. So right, this is the square root of hyperbolic cosine squared x. Or you can multiply it out, right? You can multiply it out and see that you get e to the 2x plus 2 times e to the x times negative e to the negative x, which is just -1, and then plus e to the negative 2x. And this is the same thing we've seen happen a million times. 1/4 times -2 is -1/2. So I've got 1/4 e to the 2x minus 1/2 plus 1/4 e to the negative 2x. Then you add the 1 to it, and you add this 1 to this here. That changes the positive. It factors back out where the sign in the middle changes, and that's exactly this. So you write it like this, or if you prefer, you can write it like this. They're the same. They're just one. It's kind of like how natural log is an abbreviation for log base e. Hyperbolic cosine of x is an abbreviation for e to the x plus e to the negative x over 2. All right, and then the rest of it is not too awful. You anti-different, well, you simplify. If the square root of a thing squared is just the thing. So, right up here. So we end up with the integral from negative c to c of e to the x plus e to the negative x over 2 dx. And then we have to differentiate that, or you can just say it's or it's the integral of hyperbolic cosine. The integral of hyperbolic cosine is positive hyperbolic sine from negative c to c. Or here it's e to the x over 2 minus e to the negative x over 2. Negative c to c. So either way you do it, then you're going to plug in your c's and set it equal to 6 and then solve for c. Sounds like it's still hard at the end. So I should talk about that because it's kind of not the easiest thing. So let's talk about solving this equal to 6. Because although it might seem like it's not too terrible, it's pretty terrible. Okay, so we're solving e to the x over 2 minus e to the negative x over 2 from negative c to c equals 6. And plug in c. And multiply both sides by 2 because I am smart. So e to the x minus e to the negative x from negative c to c equals 12. So then e to the c minus e to the negative c minus e to the negative c minus e to the negative c equals 12. So it's e to the c plus e to the c, so that's 2e to the c minus 2e to the negative c equals 12. Holy smokes, that looks weird. How do we solve that? It's tricky. First, divide everything by 2. and then bring the 12 over to the, well, the 6 over to the left. So I'm going to have e to the c. I'm going to subtract this over. I'm going to say it's 6 divided by 2. So minus 6 minus e to the negative c equals 0. All right, so check this out. I'm going to multiply everything by e to the c. So if I multiply everything by e to the c, I'm going to have e to the c squared minus 6 e to the c, and e to the c times e to the negative c is 1, which is because e to the 0. And look, now you've got a quadratic equation in e to the c. That's like something squared minus 6 times something minus 1 equals 0. So we can solve for e to the c using the quadratic equation. It's going to be negative b plus or minus the square root of b squared minus 4 times a, which is 1, times c, which is negative 1, all over 2 times a. So e to the c equals 6 plus or minus the square root of 36 plus 4, which is 40, all over 2. Take the natural log of both sides, and c is equal to the natural log of this, except you can't have the minus 1, because 6 minus root 40 is negative. Well, that's insane. I will address, okay, I feel like I went down the wormhole of arc length, and I kind of probably am not going to get out of it, but I will try to. So, crazy problem. The other problem that's asked about this is slightly less crazy. So let's address that one real quick, because I think that one is maybe a little more doable. So the other question is, find the surface area for, I'm going to do it y equals hyperbolic cosine of x, where x is between 0 and natural log of 7. And revolving around the y-axis. Sure. So if we're around the y-axis, that means our radius is x. Which seems kind of crazy. These problems are bonkers. Yeah. I feel like I need to make sure that that's right. Sorry, one sec. Okay, yeah. I think I'm gonna, so the person that asked me the question and the thing, I'm happy to discuss it in office hours, but I feel like I'm about to make some terrible mistake here and I don't want to, and just throw everybody off in a weird direction. So feel free to come ask me about this one. But the idea is going to be very much similar, right? You're going to find your ds in the same way. And here I will say, right, if y is equal to hyperbolic cosine of x, your ds is going to be the square root of 1 plus hyperbolic sine squared, which just ends up being the square root of hyperbolic cosine squared, which is just hyperbolic cosine. The problem is, the problem is if you're going around the y-axis, then your radius is x, and I'm not sure how to integrate x times the hyperbolic cosine of x. And maybe I'm reading something wrong, which is why I don't want to get too caught up in this one. So, arc length and surface area. Yes, it can be complicated, but the formulas are kind of all the same. It's always the integral for surface area. It's always the integral 2 pi r ds. You just have to make sure you know what your radius is and what your ds is. And I will once again stress, doesn't matter. I mean, we are not limited by what axis we are going around. Whether you're going around the x or the y-axis, you can use whichever variable suits your needs. You just have to be careful about what your radius is depending on what variable you pick. All right. Yeah, so for the person that had that question, feel free to shoot me an email or come to office hours or something. That question is bonkers, but not that bonkers. All right, so let us finally start talking about some. Oh, there was one other thing. Yeah. I don't think we're going to get to the fluid force question today, but we'll definitely start talking about work. So, work. Very, very generically, work is force times distance. When I think of force, I really think of weight. Right? Because force is mass times acceleration. In the US system, that's going to be, force is going to be measured in pounds. Mass is not a great unit for mass, it's slugs, which is terrible. Acceleration is in feet per second squared. In the metric system, weight is given by, or force is given by newtons, and it's mass times acceleration, which is kilograms times meters per second squared. Distance, feet or meters or whatever. So that's kind of the idea, the very, very broad idea that work is force times distance. So let's talk about springs. Springs are usually where we start with these work examples. And yes, I know we're not going to get to all the work stuff today. Don't worry, we'll definitely talk more about work on Thursday. Let me see if I can grab the problems I want to show you. Where did you go? Sorry, everything's hiding from me. Sorry, I was really thought I had a thing all ready to go. There we go, found it. Cool. So when you stretch a spring out, the more you stretch it, the harder it becomes to stretch it. Or said more mathematically, the force required to stretch the spring is proportional to the distance it's stretched. The further it's stretched, the more force you have to use to stretch it. Also, it's also true for compressing it, right? Although compressing is not, I feel like I'm not as good at visualizing. Like if you've got a spring, I guess you can compress it a bit, and the more you try to compress it from its natural length, the greater the force required. So Hooke's law says that the force required to stretch a spring a length of x beyond its regular natural length, or compress x beyond its natural length, is proportional to the length stretched. So, right, there's the force required, and x is the length different from its natural length. Okay, and k is the spring constant. So let's look at an example. And I kind of feel like I should, yeah, we'll see. So, yeah, if 20 newtons is required to stretch a spring of force, I don't love the wording there. Sorry. It's required to, no, I'm fine. It's required to hold a spring stretched 2 meters beyond its natural length of 5 meters. What's the spring constant? Okay, well, that's easy enough. We know that force is proportional to distance it's stretched. So our force is 20 newtons. Our spring constant we're going to solve for. And our distance x is 2 meters. Right? We don't care about what the lengths are. We just care about how much difference in length. So our spring constant k is 20 over 2, which is 10. And I guess you could say it's 10 newtons divided by meters. I don't really ever think about the units for the spring constant. But yeah, you could if you wanted to. It's kind of like, well, because newtons, right? Newtons are mass times acceleration. That's kilograms times meters per second squared. So newtons divided by meters is like kilograms per second squared. That seems weird, right? I'm not going to worry about that, those units on the spring constant. The more interesting question is, how much work was done when we stretched the spring from its natural length of 5 meters to its extended length of 7 meters? So how much work is done stretching from 5 meters to 7 meters? So I always like to draw a picture for these. So here's my spring, it's looking springy. And here's its natural length of 5 meters. And here's its stretched out length of 7 meters. For this one where you're working from its original length, it's not as much work, but work, pun intended. It's not as challenging to do the problem or to set it up, but it's still good to kind of use this framework. So we can't just say that it's 20 newtons times 2 meters, right? Because the force isn't the same everywhere, right? To stretch it a little bit, you only need a little bit of force. To stretch it more, you need more force. So each little section, stretching it requires a different amount of work. So if I look at this little section right here, right, this section has a length of, I'm going to say dx, and it's getting, so the work done to stretch gosh, words are failing me here. So the work to stretch it just over that little dx part there is going to be, so I'm sorry, my words are getting caught up. We're going to kind of make the usual assumption we make when we've got a really, really small section of something. We're going to say that in this small section, the force there is essentially constant. And we know that the force there is k times x, where that's your x. So the work there is going to be k times x, that's your force, times your distance, which is dx. So that's the work that we're going to do when we stretch it just from here to there, over that little tiny bit. But then we want to know the total work. So we're going to add up all of the work. So we're going to, whoops, darn it. Sorry. So we're going to do like from here to here. We're going to do, okay, well, it's going to be whatever the force is, k times x, where x is much smaller here, times dx, and so on and so on. So to get the total work, we're going to add up all of the little pieces of work from as far left as x equals 0, right? Because if we're starting at 5, well, the amount of displacement or the amount of stretching is 0 to x equals 2. So typically what I do is the natural length I call x equals 0, and then any other lengths I think of in reference to that. And we found k was 10, I believe. We did, yes. So we're going to integrate 10x dx. Force times distance. The integral for these spring ones is usually pretty easy. right? Iterating this is like, okay, no big deal. It's 10x squared over 2 from 0 to 2, which is just 5x squared from 0 to 2. So that's 5 times 4 minus 5 times 0, which is 20. 20 joules of work. Because the amount of work we've done is newtons, right? Force times distance is newtons times meters, which is measured in joules. Okay. How much work if I want to stretch it another 2 meters? If I want to stretch it from here to here, how much work is that going to take? Well, I'm going to be integrating the same thing, but now, what are my limits of integration going to be? You're close, Rodrigo, and maybe I didn't phrase the question very well. If I want to stretch it from the original length to 9, you're totally right. But I want to stretch it. I'm saying I want to stretch it an additional 2. So I want to start here with it already being stretched out to here and stretch it to a length of 9. So your upper limit is totally correct, but your lower limit isn't quite right. The lower limit is going to be just 2. Right, exactly. And so in this case, again, the integral is pretty straightforward. It's going to be 10x squared over 2, so 5x squared from 2 to 4, which is going to be 5 times 4 squared, so 5 times 16 minus 5 times 2 squared. And that's going to be 5 times 12, which is 60 joules. So notice, it took more work to stretch it further out, right? The first 2 meters I stretched it only took 20 joules of work. The next 2 meters I stretched it, an equal distance of stretching, took 3 times as much work, 60 joules of work. How did I get the 4? Good question. I didn't draw it. So here's x equals 0, here's x equals 2, and I said I wanted to stretch it an additional 2 meters. So that's going to put me at, well, 0 plus 2 is 2 plus 2 is 4. Like that. Okay, there is another type of question. Well, I should say, so usually there's 2 ways of phrasing these spring questions. One way, like we've done, with say, okay, it takes this much force to hold the spring at a certain length, which allows you to calculate the force constant K. Now tell me how much work it takes to stretch it from here to here. But there's another way of phrasing this that sounds similar, but is a little bit different. So let me show you an alternate version of this type of question. And I don't have any, I do have a question over here, actually. Let's see. Where'd you go? Why am I hiding things from myself? Darn. Okay, fine. So here's the other way. It takes, let's see. I'm just going to make up numbers and hope they come out right, which is probably, it's probably going to be a little bit ugly. That's right. So let's say it takes 10 joules of work to stretch a spring from its natural length of 50 centimeters to a length of 75 centimeters. How much additional work does it take is required to stretch from 75 centimeters to 100 centimeters? First things first, you don't want things in centimeters. You want things in meters so that your answer will be in Newton meters, which is also known as joules. So I'm going to change these things to meters, which is just moving a decimal place over. So here's what we're kind of doing. We're being told it takes so much work to stretch from 50 centimeters to 75 centimeters. Right? It takes, how much did I say? 10 joules of work? 10 joules. So it takes 10 joules. And then we're being asked how much work it takes to get to 100 centimeters. So what I'm going to write up here is, okay, 50 centimeters, that's the natural length. That's x equals 0. Right? That's 0 amount of stretching. 75 centimeters is stretched out 25 centimeters or 0.25 meters. And finally, 100 centimeters is going to be 0.5 meters stretched. Okay, but this isn't the hard part. The hard part is, last time I told you it took so much force to hold it. And so we said, oh, okay, well, force is whatever it is. It's equal to k times x. We know force, we know x, solve for k. That's not what we've been told here. We've been told it takes 10 joules of work to stretch it from here to here. Right, so this took 10 joules of work to stretch it. Well, I know how to calculate work. It's an integral of force times distance. So what I really have to say here is that, oh, so the work in stretching from x equals 0 to 0.25 of my force times my distance, right, where my force is k times x, that's going to equal 10 joules. So this is the difference. If they tell you how much work it takes, you'd be like, oh, I find work with an integral. I'm going to set the integral equal to the amount of work they told me it was and solve for k. If they tell you how much force it takes to hold the spring stretched a certain distance, that's when you just get to say, oh, force equals k times x. We know the force, we know the x, we're going to solve for k. So hopefully that's a clear difference. If they tell you work for a spring, you got to use an integral to solve for k. If they tell you force for a spring, you got to use just this equation to solve for k. So we're going to get, let's see, I'm going to get k times the integral of x is x squared over 2 from 0 to 0.25 equal to 10. And hopefully the numbers I chose aren't too terrible. So let's see. So here's what I've got. I'm going to multiply both sides by 2. So k times 0.25 squared equals 20. So k equals 0.25 squared is 1/16, right? Because it's 1/4 squared versus 1/4 times 1/4. So we've got 20 divided by 1/16, which is 20 times 16, which is 320. So that's my spring constant, 320. And now we're being asked to find the work it takes to stretch from here to here. So we're going to do the same integral of k times x, except instead of from 0 to 0.25, it's going to be from 0.25 to 0.5. So this work right here is going to be the integral from 0.25 to 0.5 of k, which we just found to be 320. Sorry, 0.25 to 0.5 of 320 x dx. And then we'd integrate that. Luckily, these spring ones are always pretty easy to integrate. Like literally, it's almost always just something times x. So the integral of 320x is 160x squared, or 320x squared over 2. From, I'm going to try and use fractions instead of decimals, from 1/4 to 1/2 instead of 0.25 to 0.5. So that when I plug that in, I get 160 times 1/2 squared, which is 1/4, minus 160 times 1/4 squared, which is 1/16, which ends up being 104th. 160 times 1/4 is 40. 160 times 1/16 is 10. So I get 30. So it took 30 joules of work here.
there's probably something going on here about why it was 3 times. Like, so both of these times, oh, sorry, I erased the one. I did some original length from the natural to somewhere, and then I did that same length again. And the next part was always triple the first part. There's probably a good reason for that. It's probably not just a coincidence, but the point is really it takes more work, right? To stretch it from some length here or some further length here, even if those lengths are the same, since we're stretching it further out over here, it takes a lot more work to do that. Oof. All right. I think that is all I've got for you guys today.